What is artificial intelligence? Actually, this is a question which is harder to answer than it might seem at first. When asked about artificial intelligence, the average man on the street usually thinks of some sort of robot, specifically some sort of metal man that walks the street doing whatever metal men do. Undoubtedly, robotics is a very important part of AI, and increasing in importance as robots are becoming more and more practical. But it's still only a very small part, and indeed, most of the robots that exist don't resemble human beings at all. They are less likely to look like this, and more likely to look like this. I needn't point out that the whole purpose of this series of videos is to give you some hands-on experience with artificial intelligence, but I have no plans to teach you how to build a robot. If we're going to get a handle on what AI is, we could do worse than to look it up in the dictionary. I don't touch Google, so I looked on DuckDuckGo. Artificial intelligence, sometimes called machine intelligence, is intelligence demonstrated by machines. Well, no kidding, Sherlock. In contrast to the natural intelligence displayed by humans and other animals. In computer science, AI research is defined as the study of intelligent agents, any device that perceives its environment and takes actions that maximize its chances of successfully achieving its goals. Well, I suppose that's a fair attempt at encapsulating AI, but it's not very satisfactory if you think about it. Intelligence demonstrated by machines. Well, we think we would recognize intelligence in human beings. If a human being could add up 100 numbers accurately in a fraction of a second, we would probably call him intelligent. A spreadsheet can do that, but we don't classify spreadsheets as part of AI. On the other hand, when we open our eyes, we immediately recognize what we see in front of us. Even if we're in a new location, we generally know what the things are that we see. Tables, chairs, letters on a screen, and so on. We wouldn't regard that as intelligent behavior in humans, probably because we all take that ability for granted. But object recognition and scene analysis definitely counts as AI. A 2-year-old can toddle effortlessly across a room, and we would hardly call that an intelligent act. But to get a machine to do the same thing requires a vast amount of computer programming. Personally, I prefer the definition of artificial intelligence that my old university professor gave, although he might have had his tongue somewhat in his cheek when he gave it to us. His response to the question, "What is artificial intelligence?" was, "Well, we'll know it when we see it." Perhaps one way of defining artificial intelligence is to list at least some of the topics that it does cover. They're not in any particular order, and don't be surprised if I miss one or two. I'm doing this off the cuff. Speech recognition. This is the aspect I was working on when I studied for my MPhil at Southampton University. We like to think that recognizing the spoken word is easy, but the variations in speech intonation and accent make it fiendishly difficult for computers. Even so, we are starting to see things like semi-intelligent agents answering telephone queries and machines transcribing dictation. Image recognition and scene analysis. This is an even harder problem, as it increases the number of dimensions from 1 to 2. Image recognition involves identifying objects in a scene, whereas scene analysis takes those identifications and uses them to work out what's going on in an image. For instance, the computer could use things like the rules of perspective to estimate how far away in an image the object is, and by comparing one image with another a short time later, how fast it is travelling. One of the most useful subfields in AI research is the processing of natural language, originating from some of the earliest work in computing involving the analysis of grammars of programming languages. We are starting to see applications on our mobile phones that will translate foreign languages into English and vice versa. Other uses involve holding unstructured conversations with people, to the extent that machines are starting to replace humans in places like call centres. Logic processing is a catch-all term when premises are turned into conclusions. It is the sort of reasoning that we are all familiar with, from logic syllogisms, where we are told that Polly is a parrot and that all parrots are birds, and we conclude that Polly must therefore be a bird. More practically, a program could be fed information on, say, a particular family tree, and then asked to draw conclusions about it. If it is told that Peter has a sister called Sandra, then it could reasonably conclude that Peter is Sandra's brother. Theorem proving is very similar, except the logic processing is applied to heavily structured fields like mathematics. Since the rules of mathematics are rigorously logical, computers have made huge strides in proving mathematical theorems that are beyond the power of human mathematicians to do so. Game playing. Getting a computer to play competitive games such as chess and backgammon competently against a human opponent. This has been one of the great successes of artificial intelligence, possibly because board games are played in such restrained environments. You have computer programs that can beat world champions in these games, and the sight of a machine playing chess against a human is used so often to represent AI itself that it's almost become a cliché. Decision-making and planning is one of those covering topics that appears to some extent in all these categories, not only in systems designed to offer advice in specific situations, but also in things like autopilots on airplanes. Self-driving cars and control systems in complex systems like nuclear reactors also need to make decisions, life-critical decisions. Planning is also called goal-seeking and comprises the stringing together of several decisions in order to reach some specified goal. The program is given a target point or state and has to work out the best way of getting from where it is at the moment to where it wants to be. One of the earliest successes in AI, alongside game playing, was expert systems. These work in various specialized fields, diagnosing problems, and were generally intended to encapsulate the expertise of specialists and deliver it to non-specialists. For instance, an early expert system called Mycin was created to diagnose blood disorders and put the training of expert hematologists in the hands of ordinary doctors. Another one, called Prospector, correctly predicted the presence of large quantities of molybdenum ore under New York City. Representing knowledge is another one of those umbrella topics that appears in several forms in various others. It involves creating an internal representation of the outside world, or at least particular parts of it, and specifying the relationships between objects in that world. For example, in that syllogism above, Polly will be linked as an example of parrot, and parrot will be linked as an example of bird. When asked, is Polly a bird? The system will trace the lines on its internal diagram and respond, yes. Simulating the brain. Yeah, this is kind of the poor cousin on the artificial intelligence family tree. I'm not referring to neural networks or deep learning, which are great successes and possibly represent the most promising field of AI at the moment. No, simulating the brain means making computer models of small aspects of human psychology, such as the attention mechanism or parts of the visual cortex, and seeing how they behave under various circumstances. Quite often this means inhibiting or crippling the model in some way to see if it then mimics some human disability or cognitive problem. You might well ask what use is this? And that is a very good question. Modelling the brain doesn't help improve surgical procedures to correct such problems in the human brain, or help develop cognitive therapy. The best that can be said is that it gives us some unspecified insight into human behaviour in some way, and at least the animal rights people don't complain when we experiment on computer models. I suppose the holy grail of simulating brain processes in a computer is to crack the secret of human consciousness, or even, in the very distant future, to create a conscious machine. Needless to say, we are nowhere near either of these goals. Pathfinding is very similar to decision-making. The most obvious example is finding one's way through a maze or around a physical map of streets or paths, but it also refers to planning the best route across a map where the circles on it represent different states or conditions of a system, and the arrows linking them are the possible actions to take you from one state to another. In either case, you are at point A on the diagram and you want to get to point B, finding the optimal route to do so. And lastly, we have creativity. This is a controversial topic, as many people can't accept that a programmed machine can create anything truly novel or original. Nevertheless, computer programs do exist that write poetry, compose symphonies in the style of Mozart, even paint original works of art. Whether these are truly creative or innovative is a point closely argued in the AI community, but such programs do exist, and they are getting more and more sophisticated all the time. There you are. I can't think of any AI applications that don't fit into any of the categories above, but if I have missed anything, I don't want to hear about it in the comments. Many AI systems don't fall nicely into one or other of these categories without any crossover, however. For instance, an electronic eye, whose purpose is to read the addresses on mailed envelopes, must locate all the writing on an envelope in its field of view, which is a form of image processing, and then analyse that writing to determine whether it's a correctly formed address, which is a form of language processing. You'll notice that one topic conspicuously absent from that list is general intelligence, the ability to act intelligently in a variety of situations, responding to many different stimuli as and when they happen. This is the holy grail of artificial intelligence research, and is, at the moment, nothing more than a pipe dream. Instead, the history of AI research is a series of special cases, of systems dedicated to single purposes, with little effort to tie them all together in one unified whole. Having said that, we are starting to see the first early steps into general AI in the form of androids, which are robots vaguely shaped like human beings. You've probably heard of Asimo, produced by the car manufacturer Honda, but there are others, such as Atlas, produced by Boston Dynamics. These machines can move around, interact in simple ways with human beings, such as conversing with them, and carry out basic tasks, like fetching and carrying objects. However, they take vast amounts of money and years of engineering to make, so it's generally only large companies that can afford to do the research. Even then, these things are little more than vanity projects. Honda, for instance, are not intending to mass-produce Asimo robots for sale to the public. Asimo's only function seems to be to demonstrate what the company is capable of at motoring and technology expositions. No introduction to artificial intelligence would be complete without at least a mention of the Turing Test. In 1950, Alan Turing, one of the most eminent pioneers of computing, proposed a test by which we could judge whether a machine could be classed as intelligent. The actual Turing Test, as outlined in his seminal paper, so seminal that I've yet to come across anyone else who's actually read the thing, is rather complicated, involving 3 participants, 2 humans and the machine being tested, but it's usually given in this simpler form. A person is communicating via 2 keyboards and 2 screens with a machine and another human. The person can make any statement or ask any question that he likes to either or both correspondents, and both human and machine reply as they think fit. If, after a certain length of time or a certain number of interactions, the person can't decide which of the 2 is the machine and which is a human being, then that machine can legitimately be referred to as intelligent. At the moment, we don't have any computer program that can pass the Turing test, although you'll come across various websites containing chatbots that give it a go. You type in what you want to say to the chatbot, and it responds as best it can. Generally, it doesn't take more than 2 or 3 sentences before these bots start producing nonsense. They are nowhere near convincing a person that they are really human. However, there have been cases where a computer program has managed to fool a human being, provided that the context is severely limited. Here's a quick example which we can try right now. On the screen, you can now see 2 poems. One was written by a human being and one by a computer. Pause the video and read them through once or twice. Then ask yourself 2 questions. Firstly, which poem do you prefer? Which is better in your opinion? Personally, I think they're both drivel, but then I'm a complete Philistine with no poetry in my cold, dead soul. Secondly, and more importantly, which poem do you think is written by the computer? It will be interesting to hear your, well, I don't like to use the word guesses, in the comments below. Go on, nail your colours to the mast. You know you want to. Rather amusingly, I can give a personal example of a computer program passing a restricted Turing test as well. Years ago, I used to give private tuition in mathematics and English, and I illustrated a lesson I was giving on story structure by giving my pupil a copy of a simple computer program that wrote romantic fiction stories. All the user had to do was provide the name of the hero and the name of the heroine, and the computer would do the rest. A week later, the pupil told me that he'd taken the story that the computer had produced, put his own name on it, and submitted it to his teacher. She gave him an A+ grade for his work and complimented him in front of the entire class, although she had to admit she couldn't quite understand why a 10-year-old boy would want to write romantic fiction. It was brilliant. I don't think he ever came clean to her. Anyway, Moving on. Can computers think? The answer is no, at least not yet, but it doesn't matter. The important thing is they carried out actions which appear intelligent to us and perform some useful function, even if that is only to amuse us for a few minutes with a game of tic-tac-toe. Artificial intelligence is, at best, merely the blind carrying out of instructions by a predictable, programmable machine. While computers can increasingly appear intelligent, they are not. For example, a computer program designed to distinguish between pictures of cats and dogs has no internal concept of either animal. The philosopher John Searle proposed a thought experiment called the Chinese Room in 1980 to demonstrate how artificial intelligence can produce useful results without involving consciousness or a mind in any way. His argument went as follows. Imagine that a person sits in a room and only has contact with the outside world through two slots in the wall. The person receives pieces of paper through one of the slots with Chinese characters on them. The person in the room has a vast book which lists every possible legal combination of Chinese characters, effectively every possible sentence in the Chinese language. And next to every one, there is another sentence in Chinese which represents a suitable response. This person is special in the sense that in less than a second he can find the incoming sentence in that huge book and then copy out the response on the other side of the piece of paper and pass it out through the second slot. The person in the room has no knowledge of Chinese. All he does is find the sentences he receives in this book and copies out the responses. However, the people in the outside world don't know this. They write complex sentences in Chinese, pass them into the room, and receive suitable responses, also in Chinese. They would naturally conclude that whoever was in the room did speak fluent Chinese. Clearly, the Chinese room represents a computer program, and indeed, it would be feasible to provide such a program with responses to a large number of input sentences, although not every sentence in the entire language, of course. It is a simple matter to associate each input with the appropriate output, in which case it might appear to be fluent in Chinese. However, as we will see in a later lecture, it would only appear intelligent on a most superficial level, and even then not for very long. Hubert Dreyfus, a notable skeptic of the field of AI, at the Massachusetts Institute of Technology, was particularly critical of the idea that computers could understand the world around them. On the television series The Dream Machine, in 1991, he had this to say. So you get a blood disease analysis program. It's brilliant at deciding which blood disease the patient has on the basis of a lot of objective tests. But if you ask it, what is a germ? It doesn't have the slightest idea. Or what is a patient? Or do people prefer to live or die? It breaks down. That's the brittleness. Clearly, Dreyfus believed that general AI would never be possible. I'll definitely mention him again when I upload my lecture on the philosophy of artificial intelligence. And on that depressing note, I will end this lecture. Accompanying this video is Code Part 1, which is a JavaScript rendition of Menace, a system developed by AI researcher Donald Mickey to play tic-tac-toe. Please do follow the link in the description below. Also, if it's the first of my lectures that you've seen, don't forget to like the video, comment, and of course, click the subscribe button. Thank you.